I'm Ahmad Aljaber. I'm a PhD student with the Professor George Protevsik. Today I'm going to talk about functionalized polyethylene. Um, well, as you know, polyethylene is one of the most produced polymer, and polyethylene has a very good physical and chemical properties. However, polyethylene has limited applications, and that's mainly due to the low polarity and poor adhesion. Well, what is this poster about is about synthesizing an additives that has an antimicrobial properties, utilizing the catalyzed chain growth mechanism or route that I'm gonna explain later on. We were able to synthesize antimicrobial agent and attach them on different molecular weights of alkane. You might ask why this is important. Well, if we just mix antimicrobial agents with polyethylene, they will leach out over time and they won't stay in the polyethylene matrix. However, while we synthesize the antimicrobial alkane or antimicrobial active agents on alkane, these alkane can entangle into the polyethylene matrix and then can be used as additives. How can we achieve that? Well, as I said before, we utilize the catalyzed chain growth that is in section number 3. If you can scroll down a little bit, Leah, thank you. Yeah, if you can see section number 3, we have the methodology that we use, where we use the ion-based catalyst with MAO as a co-catalyst and diethyl zinc to synthesize different molecular weights of alkane. Alkane on zinc. This mechanism will produce a polymer with a narrow molecular weight distribution that can be easily functionalized to different functionality, as you can see in scheme number 1. Leah, if you can go up to section number 4, please. Thank you. Since we synthesize the since we synthesize the alkanes with different functionality, we're able to change the functionality and synthesize two antimicrobial into these alkanes. We chose chlorhexidine and octadienine dihydrochloride. As you know, these two antimicrobial are effective against gram-positive and gram-negative bacteria. They have distinctive properties, which made them a good candidate to be used in this research. Also, they can be used in wide applications in the medical appliances or in the oral hygiene etc. If you can go to section 5, please, Liam. Thank you. Can you please enlarge on the figures? Thank you, appreciate it. Well, here we can see figure 1, where we have the carbon number or the molecular weight against the yield at different molecular weights in different functionalization steps, and we can see that the yields is actually decreasing as we increase the molecule weight. In figure 2, we can see that a confirmation it's a proton NMR to confirm the change of the functionality in each step. In figure number 3, we can see the proton NMR for chlorhexidine, which matches similar structure in the literature. In figure 4, that's a one proton DOSI NMR, and that's just to confirm that the two segments, the alkyl chain and the antimicrobial agents, the chlorhexidine, are actually chemically connected, where you can see that the diffusing take place at the same time. Can you please go to section 6, the last one? To conclude here, we have synthesized 2 antimicrobial alkane. However, we haven't been able to test them yet, and that's our next step. These alkane will be extruded. These antimicrobial alkane will be extruded in a commercial polyethylene to form a composite and test for antimicrobial and migration of these antimicrobial agents. This work can be extended to a different application by replacing the polyethylene to polypropylene. Thank you, everyone. And if you have any question, you are welcome.